Welcome friends once again to the paper of numerical methods in the subject of information technology under EPG Pathshala. In our previous module, we learned about roots of polynomials. We got the idea that why do we need to study about roots of polynomials specially once we have learned to find the roots of an equation f x equal to 0. And basically in our previous module, we learned that polynomials need spatial treatment and they can be given spatial treatment because they have complex roots. We have fundamental theorem which tells us that polynomial of degree n has exactly n roots and the roots may be real or the roots may be complex, and whenever the roots occur, complex roots occur, they occur in pairs. And basically in our previous module, the methods which we learned were the methods to find the location of the real roots of a polynomial, and specially we focused on Descartes' rule of sign, Boudin's theorem and Stump's theorem. See, a polynomial with real coefficients can also have complex roots. So, today we shall focus on how to locate complex roots of a polynomial. Now, see, for locating complex roots of a polynomial, the first question which arises is how to say a complex root lies between so and so. In case of real numbers, we say okay, root lies between -4 and -3. In case of complex numbers, you are very well aware that complex numbers cannot be ordered. And so, I cannot say a complex number has to lie between this and this complex number or between this or this real number. So, how to tell about the location of the complex root? See, complex number is of the form a plus ib, where a is real and b is real, and this is represented in a coordinate plane as the ordered pair ab. And so, its distance from y axis is a units and distance from x axis is b units. So, a complex number, if you want to measure, it is measured as its distance from the origin. If I join the point line from origin to the complex number a plus ib represented by the point ab, then this line has the length of this line is square root a square plus b square. So, this is how we can tell that a complex number lies from distance from the origin at such and such value. So, this is how we will give the location of the complex roots. Now, the first result which will talk about the location of the complex roots is, let us take the polynomial p x as a0 plus a1 x plus a2 x square, so on, a n x raised to n, a n different from 0. So, it is a polynomial of degree n with real coefficients. So, this result says that it has at least one root which may be real or complex within the circle of radius r1. This circle is about origin, complex plane, that is a coordinate plane a axis and b axis, and this radius r1 is given by the minimum of two numbers. The first number is a0 by a1, see a0 and a1 are real, take the ratio and absolute value of that multiplied by the degree of the polynomial n. And the second number is a0 by coefficient of x raised to n, that is a n, again take the absolute value and take the nth root of that, and minimum of these two numbers is given by r1. And it says that at least one root of the polynomial will lie inside mod z, means it is z is x plus I y, absolute value of z is square root of x square plus y square. So, x square plus y square less than equal to r1 square, that means it lies inside the circle of radius r1 when the circle is drawn with center as origin, and so at least one root will lie at a distance of within the distance of r1 from the origin. And it also says that all the roots of the p x should lie within the circle of radius r2. So, they will lie in the region mathematically defined as absolute value of z is less than equal to r2, where r2 is given by the number, it is 1 plus we take the set of values ai by an, means a0 by an absolute value, a1 by an, a2 by n, so on, and find the maximum of this where I ranges from 0 to n minus 1. So, a0 by an, a1 by an, a2 by n, so on, an minus 1 by n, absolute sign and maximum value of that number plus 1, and so one root will lie inside this circle of radius r2. Let us take one example. Let Px be minus 6 plus 10x minus 6x square plus 4x raised to 4. It is the same polynomial which we have taken earlier in our previous module. So, what are the values of here? Let us compare this with our polynomial Px is a0 plus a1 and so on. So, the degree of the polynomial n is 4, constant term a0 is minus 6, coefficient of x is a1 given by 10, coefficient of x square is a2 given by minus 6, coefficient of x cube is 0 given by a3, and coefficient of x raised to 4 is a4 given by 4. Let us apply our bound formulas. So, r1 we know is given by a. So, let us form this expression a0 by a1 and a0 by an. See, n is equal to 4. So, let us substitute, we get the value r1 is minimum of 4 times a0 by a1 absolute sign and 4th root of absolute value of a0 by a4. Now, let us substitute a0 as minus 6, a1 as 10, and absolute value gives 6 by 10, 4 into 6 by 10, and the other term is a0 by a4, that is minus 6 by 4, absolute value gives 6 by 4 and 4th square root, quadratic root of that. So, 6 by 10 is 0.6, 0.6 into 4 is 2.4. and 6 by 4 is 1.2, 1.5 and 4th root of that. So, it is minimum is 2.4 is bigger than 1.5. So, minimum of 2.4 and 4th root of 1.5 is 4th root of 1.5, which gives us 1.1067. So, the result says that at least one root will lie within a distance of 1.1067 from the origin. Let us apply the second bound, that is r2. R2 is 1 plus maximum of absolute value of ai by an, where I is between 0 and n minus 1. So, in this example R2 becomes 1 plus maximum of n is 4 here. So, absolute sign a0 by a4, a1 by a4, a2 by a4, a3 by a4, and substitute the values. A0 is minus 6, a1 is 10, a2 is minus 4, a3 is 0 and a4 is 4. So, it gives us absolute sign 6 by 4, 10 by 4, 6 by 4, 0, maximum is 10 by 4. So, it is 1 plus 10 by 4, 10 by 4 is 2.5. So, the answer is 3.5. So, the result is at least one root lies within a distance of r1 and all the roots lie within the distance of r2 given by 3.5. So, this is how the diagram looks. One root lies between r1, that is between this circle of radius 1.1067 from origin, and it ensures that all the roots will lie within the distance of 3.5 from the origin. So, inside the bigger circle all the roots will lie, that is within a distance of 3.5 from the origin, and inside the smaller circle at least one root should lie. We have another result, and before we take the another result, let us take another example, that Px be x raised to 5 plus 5x to 4 minus 20x square minus 10x plus 2. So, here the polynomial degree is 5, n is 5. So, in our this other example, n is 5, a0 is 2, a1 is minus 10, a2 is minus 20, a3 is 0, a4 is 5 and a5 is 1. And so, r1 is given by minimum of 5 times a0 by a1 in absolute sign and 5th root of a0 by a5 under absolute sign. So, let us substitute these values. This gives 5 times 2 by 10 and 5th root of 2 by 1. 2 by 10 is 0.2, 0.2 into 5 is 1 and 5th root of 2 is 1.14. So, minimum is 1. So, this tells us that there is at least one root within a circle of radius 1. Let us calculate the upper bound, that is r2. So, r2 is 1 plus maximum of ai by a5 absolute sign, where I is changing from 0 to 4. So, absolute value of a0 by a5, absolute value of a1 by a5, absolute value of a2 by a5, absolute value of a3 by a5, absolute value of a4 by a5. And let us substitute these values. A5 is 1. So, just it gives A0, A1, A2, A3, A4. So, that is 2, 10, 20, 0, 5, 1. And so, it is maximum is 20 here. So, 1 plus 20, this gives the answer 21. So, we can say that all the roots lie inside the circle with the radius 21, that is mathematically mod z less than equal to 21, and at least one root will lie within a circle of radius 1. There is one more very important result which is known as Cauchy's theorem, which can also be used to establish bound. Let us have a look at this Cauchy's theorem. So, again we have a polynomial, the same polynomial given by a0 plus a1 x plus a2 x square up to a n x raised to n, where a n is different from 0. Now, in this case we define two new polynomials from this small p x, which we denote as capital P x and capital Q x. What is capital P x? See, capital P x is nothing but same coefficients, but the highest degree term a n x raised to n, that a n we take the absolute sign, and all other coefficients they have the same magnitude, but all are made negative. So, capital P x is given mathematically by absolute value of a n into x raised to n minus absolute value of a n minus 1 into x raised to n minus 1 minus absolute value of a n minus 2 into x raised to n minus 2, so on. Last term will be minus absolute value of a 0, meaning by first coefficient positive and all other coefficients will be negative. And the other polynomial which we denote by capital Q x, in this case all the coefficients from highest degree to the last but one coefficient of x, all these coefficients are made positive, magnitude remains the same, and the last constant term a 0 is made negative, that sign is negative. So, this is given by mathematically by absolute value of a n x raised to n plus absolute value of a n minus 1 x raised to n minus 1, so on, plus absolute value of a 1 into x minus absolute value of a 0. Now, if you look at this, see capital P x now, let us apply the Descartes rule of sign to them. We have already learned Descartes rule of sign, and so if we observe P x and see, then there is only one change in sign in P x from when we go from x raised to n to x raised to n minus 1. All other terms are negative, so no change in sign takes place. And similarly, in case of Q x, all terms are positive except the last term a 0. So, again there is only one change in sign, and so by Descartes rule of sign, P x has one positive root and Q x also has only one positive root. So, if we find those one positive root by Descartes rule, let us say the P x positive root as capital R and Q x positive root as small r, then Cauchy's theorem states that the root, all the roots of polynomial P x lie in the annular region, which is given by small r less than equal to mod z less than equal to capital R. So, they lie in the annular region given by the between small r and capital R. So, this is how it looks. The inner circle z equal to small r, outer circle z equal to capital R, and the annular region is given by absolute value of z greater than equal to r and less than equal to capital R. So, it says that all the roots will lie in this annular region. Let us take the same polynomial which we have considered in our earlier result. So, P x is x raised to 5 plus 5 x raised to 4 minus 20 x square minus 10 x plus 2. So, as we have to apply Cauchy's theorem, let us construct capital P x and capital Q x. How to construct capital P x? Except the highest degree term, all other terms are to be made negative, magnitude remains the same. So, capital P x is given by x raised to 5 minus 5 x raised to 4 minus 20 x square minus 10 x minus 2. And in the case of capital Q x, all the terms positive except the constant term will be made negative. So, capital Q x is given by x raised to 5 plus 5 x raised to 4 plus 20 x square plus 10 x minus 2. Now, we can determine, see, by any method, I have used Newton-Raphson method to determine the positive 0 of capital P x and one positive 0 of capital Q x, and that turns out to be 5.677124. There is only one positive root of Px. So, it comes out to be 5.677124 and positive 0 of Qx comes out to be 0.152938. And so, this tells us by Cauchy's theorem that the root of this polynomial Px have to lie between 0.152938, the region in the circular region having annual region between 0.152938 to 5.677124. See, this polynomial we also discussed under Sturm's theorem, and the result which we had obtained about the location of the roots of this polynomial using Sturm's theorem are reproduced here, and we had obtained that this polynomial has the root, one root in each of the intervals -4 to -3, -3 to -2, -1 to 0, 0 to 1 and 1 to 2. So, here see you look at the bound less than equal to 5.677 and greater than equal to 0.15. See, once we know this, if I just determine applying Newton-Raphson method all the roots of this polynomial, and they turn out to be -3.815861, -2.512571, -0.718595, 0.153289 and 1.893746, because we knew the location of the roots and I gave the endpoint of those intervals -1, -2, -3, -4 and 0 as the initial guesses, and using these initial guesses I could get all the roots very fast using Newton-Raphson method, and you can compare this with the bound of the Cauchy's theorem. We got one root 1.153289 and it says that the root mod z greater than or equal to 0.152938, and all the roots, the highest root is magnitude is 3.81, it gives the upper bound as 5.677124. So, this is how the Cauchy's theorem can be helpful us to get the bounds for real as well as complex roots. See, with this, once we know the bounds, we know the location of the roots, we can make the initial guesses and we can apply the other methods to find the roots of a polynomial. So, there are many methods. We would be able to take one iterative method which is known as Birge-Vieta method. See, this Birge-Vieta method is nothing but the Newton-Raphson method, but the Newton-Raphson method applied to polynomials. Now, what is the difference? It is just a question of implementation to make it more efficient. Computationally, we make it more efficient, less number of operations, arithmetic operations. So, let us take the Birge-Vieta method, and to just let us take the example how it is becoming computationally efficient. Let us understand. Let us just suppose we have this polynomial 5x raised to 4 plus 7x cube plus 4x square plus 3x plus 8. Suppose I applied Newton-Raphson method to evaluate this polynomial, and we write the function definition as it is, because Newton-Raphson method each iteration will involve evaluation of this polynomial and the evaluation of the derivative of this polynomial at a point to get the next approximation guess. So, if I just calculate this, if I give the expression as it is to be evaluated, see x raised to 4. So, x will be multiplied 3 times, x into x once, then x into x into x, then x into x into x into x, right. So, there will be 3 multiplications x raised to 4 and into 5. So, there would be 4 multiplication operations in 5 x raised to 4, x cube, x into x into x. So, 2 multiplications into 7. So, 3 multiplications, 4x square, x into x 1 into 4. So, 2 multiplications, 3 into x 1 multiplication. So, in all 3 into x 1, 4 into x square 2 operations, 7 into x cube 3 multiplication operations, and 5 into x raised to 4 is 4 multiplication operations. So, in all 4 plus 3 plus 2 plus 1 gives you 10 multiplication operations in the direct evolution of this polynomial. Addition, of course, there are 4 additions. In general, you can say that if a polynomial Px of degree n we are taking, and number of additions of course will be n, but multiplications a1 into x will give you 1, a2 into x square will give you 2, x into x 1, a2 into that 2, a3 x cube will give you 3, x into x 2 into a3, so 3, and so on. N into x raised to n will give us n multiplications, x into n minus 1 multiplication into n. So, in all n multiplications, and so the sum is 1 plus 2 plus 3 plus n, and it is very well known the sum of this is arithmetic progression, sum is given by n by 2 into n plus 1. So, it is of the order of n square. Because the method is iterative, again and again we have to do the iteration. So, every time it is order of n square multiplication operations are involved. See, the same polynomial which we considered, if you look at the expression of that polynomial 8 plus 3x plus 4x square plus 7x cube plus 5x raised to 4, the same can be expressed in this way using nested parenthesis. 8 plus 3x plus 4x square plus 7x cube plus 5x raised to 4. And if we evaluate the polynomial using this nested parenthesis, observe how many multiplications are there now. Only 1, 2, 3 and 4. There are only 4 multiplication operations, because in this nested parenthesis we are making advantage of that once we have x square, it is as good as retaining it to calculate x cube, whereas in the direct evaluation the efforts are being repeated. So, here using this nested parenthesis 4 additions and 4 multiplications. So, generally if I have a polynomial of degree n and if I use nested parenthesis, there would be only n multiplications, so order of n. So, each iteration the efforts multiplication will reduce from the order of n square, there is n square plus n by 2 to simply n multiplications. Number of additions of course will remain same, there is no change, and we also know that it will also reduce the error propagation. So, it will also reduce the amount of round of error being produced in the evaluation of the polynomial. So, it has considerable advantage in the computation, from the computation point of view, that we use nested parenthesis to evaluate a polynomial, and every iteration it is not only evaluation of polynomial, derivative of polynomial of degree n minus 1. So, there also we will use only n minus 1 operations, multiplication operations, whereas in other case it will be again the order of n square only. So, this saves computationally a lot. So, this method of using honors method for polynomial evaluation, this using nested parenthesis for polynomial evaluation is very well known as the honors method. And the method which I am going to discuss, which is known as Birge-Vieta method, is nothing but the same iterative formula of Newton-Raphson method, but the algorithm, the Birge-Vieta algorithm describes the method for using nested parenthesis technique for evaluation of the polynomial and its derivative in a very nice way. So, just let us derive that formula hurriedly. So, p x is our polynomial, derivative we denote by p dash x, and x bar with the point at which we want to evaluate the value of p x as well as derivative. So, to get the formula, the iterative formula for this, just suppose we divide p x by x minus x bar, then quotient will be a polynomial of degree n minus 1 obviously, and the remainder will be constant. So, I can express p x as x minus x bar into polynomial of degree n minus 1 as b 1 plus b 2 x b n x raised to n minus 1 and plus the constant term b 0. In this formula, if I put x equal to x bar, see the first term becomes 0. So, p of x bar is b 0. In other words, if I need the value of polynomial at the point x bar, it is nothing but the remainder value on division of p x by x minus x bar. Let us equate, see, to get b 0, let us equate the coefficients of different powers of x on both the sides. So, p x I have written as a 0 plus a 1 x plus a 2 x square plus a n x raised to n, and the right side is x minus x bar into b 1 plus b 2 x plus b n x raised to n minus 1 plus b 0. Equating power of x raised to n, if I equate, then we will get, see, the left side is a raised to n only and right side is x into the highest term x raised to n minus 1, it gives you b n. So, we get a n is equal to b n. Let us equate the power of x raised to n minus 1 on both the sides. Left side is a n minus 1 and the right side, see, we have the coefficient of x raised to n minus 1 is here x bar into b n we get, and the previous term will be b n minus 1 into x raised to n minus 2. So, b n minus 1 will get as a coefficient of x raised to n minus 1. And in general, the coefficient of x raised to I, if we equate, we will get as the formula as a j as b j minus x bar b j plus 1, because the term is x minus x bar. So, from x bar coefficient of x raised to j plus 1 and x raised to j minus 1, and so we will get a j as b j minus x bar b j plus 1. And therefore, we can write down the formula for b j's from this. b n is a n and b j is a j plus x bar b j plus 1, where j runs from n minus 1, n minus 2, 1, 0. So, to way of calculating, say if we just have a look at this, if we just illustrate this result which we have derived for n equal to 4, b 4 will be a 4, b 3 is a 3 plus x bar b 4, b 4 is a 4. So, b 3 is a 3 plus x bar a 4, b 2 is x 2 a 2 plus x bar b 3. So, it is a 2 plus x bar, substitute b 3 is a 3 plus x bar a 3 plus x bar b 4, and b 4 is same as a 4. So, it gives you a 2 plus x bar a 3 plus x bar square a 4. Now, b 1 is a 1 plus x bar b 2. So, that is a 1 plus x bar, substitute b 2, that is a 2 plus x bar in the bracket a 3 plus x bar a 4, and finally, b 0 is a 0 plus x bar b 1, and it is a 0 plus x bar, substitute b 1 expression we get. So, we get this is the value of polynomial at the point x bar of a 0 plus a 1 x plus a 2 x square plus a 3 x cube plus a 4 x raised to 4. So, this is how using this iteratively we can get the value of polynomial at the point x bar. To get the derivative is also very equally easy. If we differentiate p x, we can write p x as x minus x bar, and the term b 1 plus b 2 x plus b n x raised to n minus 1, let us write it as g x. So, I can say p x is x minus x bar into g x plus b 0. Differentiate this. So, p dash x is right side is multiplication of two terms. So, derivative of x minus x bar is 1. So, it is simply g x and plus x minus x bar into derivative of g, and b 0 is constant, derivative is 0. So, p dash x is g x plus x minus x bar into g dash x, where g x is b 1 plus b 2 x plus b n x raised to n minus 1. And from this, if I substitute x equal to x bar, I get p dash x bar as simply g of x bar. And so, the derivative can be calculated using the same technique, because derivative of p is g value of g. So, whatever technique we use to evaluate the value of p with the coefficient a's, we have to use the same technique for calculating of derivative of p at x, that is the value of g at x, that is to do the same thing with the b's now. So, we can say we get c's now, b's we got from a's. To evaluate g, we will get c's, because quotient will be term will let us have c. So, c n is b n, and the same formula, same symmetric, same parallel formula, c j is b j plus x bar, c j plus 1, j is n minus 1, n minus 2 up to 1, and p dash at the point x bar will be c 1. So, our Newton's-Raphson formula, the iterative formula becomes x k plus 1 is x k minus value of f upon derivative of f. So, x k plus 1 is x k minus value of polynomial at the point x k is b 0, and value of derivative of the value is c 1. So, this is the formula to be applied to calculate successive iterations. So, b 0 is calculated using this iterative formula, c n is b n is a n, and go on decrementing the counter, j becomes n minus 1, n minus 2, n minus 3 up to 0, and get b j's by a j plus x k b j plus 1, and c j by b j plus x k c j plus 1, j is n minus 1 to 1. Looks complex, but it is very easy to implement. We will see how. So, our algorithm now looks like we will input the polynomial p x in. So, we will input the coefficients, we will input the degree n of the polynomial, we input the coefficients a0, a1, a2, an. We input initial guess, we can make initial guess now very easily, and error tolerance epsilon, and the number of maximum iterations to be performed as we have discussed in the earlier modules. We begin the iteration. So, initial iteration initialization, our initial iteration value k is 0, and our Cn and Bn will be initialized to the same value as an, coefficient of x raised to n in the polynomial. Index of j will be n minus 1, and then it will be decremented by 1 in each counter, and bj's will be calculated by aj plus xk bj plus 1, cj by bj plus xk cj plus 1, and j will be j minus 1, and we will continue this till we reach j equal to 0. So, we get the value of b 0, then we exit. Exit means we get the value of xk plus 1, and then we repeat these steps so far as long as we reach the desired accuracy. So, if absolute value of xk plus 1 minus xk is less than epsilon tolerance, we will exit, otherwise exit and estimate of the root will be the most recent value given by xk plus 1, or otherwise we will increment the counter and we will go on. If we reach the root, fine. If we do not reach the root within our desired number of n iterations, then we will exit and with the message that the method does not converge with n iterations. So, method is exactly same as Newton-Raphson, but the method of evaluation of the polynomial and its derivative is a very efficient method using which reduces the number of operations to a great extent from the quadratic to linear, from the order of n square to order of n. Now, let us take this example and let us illustrate how to go about it. So, let us take the polynomial as x raised to 4 minus 9 x cube minus 2 x square plus 120 x minus 130. As we have done in the earlier methods, we can see that the root lies between minus 3 and minus 4, and so we can let us make the initial guess as minus 3. Here our a0 is minus 130, a1 is 120, a2 is minus 2, a3 is minus 9, and a4 is 4. Our iteration formula is xk plus 1 is equal to xk minus b0 by c1. Our bn and cn will be same as an, and iteration formula is given by bj equal to aj plus xk bj plus 1, and cj is bj plus xk cj plus 1. So, our polynomial is x raised to 4 minus 9 x cube minus 2 x square plus 120 x minus 130. So, coefficient of x raised to 4 is a4, and a4 is given by 1. Coefficient of x cube is minus 9. So, a3 is minus 9. Coefficient of x square is minus 2. So, a2 is minus 2. Coefficient of x is 120. So, a1 is 120, and a0 is constant given by minus 130. Now, we need to calculate b0 and c1. x0 we have made the initial guess as minus 3, our x0 is minus 3. To calculate b0, see this is how we are calculating, bn and cn are same as an, n is 4. So, b4 is same as a4, that is 1, c4 is also same as a4, so it is also 1. Now, let us calculate b3. How to get b3? b3 is given by a3 plus xk, xk is minus 3. So, minus 3 into bj plus 1, that is b4. So, our b4 is same as a4, c4 is same as a4, I get b4 is 1 and c4 is also 1. Now, let us calculate b3 and c3. So, b3 formula is a3 j is 3 plus x bar, that is minus 3 into b4. So, b3 is a3 minus 3 into b4. How does it look? This point b3 is a3 plus, I write here minus 3 into b4. So, minus 9 plus 1 into minus 3, I get minus 12. So, we have filled the values of AIs. b4 is same as a4, c4 is same as a4 because bn is equal to cn equal to an. Now, let us calculate b3. See, to calculate B3, it is given by A3 minus 3 into B4, A3 plus minus 3 into B4. So, minus 9 minus 3, I get the value as minus 12. Similarly, the same formula is for C also. Your C3 will be, instead of role changes. So, C3, look at the previous column. So, C3 is given by minus 12 plus minus 3 into C4. So, minus 12 minus 3, I get C3 as minus 15. Come to B2. So, B2 will be now A2 plus minus 3 into B3, A2 plus minus 3 into minus 12. So, plus minus 12 into minus 3 plus 36 minus 2, I get the answer minus 34. Similarly, if I want C2, C2 will be given by B2 plus minus 3 into minus 15, that is, it is your C2 will be given by B2, that is minus 34 and plus minus 3 into minus 15. So, it is 45 minus 34. It gives the answer 5 minus 4, it is 1, 45 minus 34, it gives 11. Now, your B1 will be B2, B1 will be C1 or B1 will be A1 plus minus 3 into minus 34. So, minus 3 into minus 34, 3 into 34, 102 and 120 minus 102, you get the answer 18. And finally, B0 will be A0, that is minus 130 plus minus 3 into 18. So, minus 54 and so answer is 4, 8, 1 with negative sign. And similarly, let us calculate C1. C1 will be B1, that is 18 plus minus 3 into 11. So, minus 33 and plus 18, we get the answer, I think minus 15. So, this is how we do not need to calculate C0, and so we get the value of B0 as minus 184. This is the value of polynomial. We will substitute here. So, x1 will be x0 is minus 3 minus B0 is minus 184, it becomes plus, and upon C1 we get the value, and this is how we get the next point x1. So, let us look at the table now, and what is the value of next iterative value x1. So, our value of x1 obtained is minus 3.840183. We repeat the iteration, same table we generate again, the same formulas we apply, and that gives us the value of x2 as in the second iteration as minus 3.621847, and continuing this way we get x3 as minus 3.600335, x4 as minus 3.600135, that is, it is becoming constant. So, the answer is correct to 6 decimal places at minus 3.600135. So, this is how the Birge-Vieta method can be very easily used to evaluate the polynomial and its derivative, and so it can be applied to calculate the root of a polynomial of degree n, any polynomial of degree n. Formula is same as Newton-Raphson method. The only thing is, in case of evaluation of the value of polynomial as derivative, we are using nested parenthesis technique, that is the Honor's method of polynomial evaluation. Similarly, if we take x cube plus x minus 1 equal to 0 with the initial guess as 0, this is how we get the subsequent values of a3, a2, a1, a0 are determined by the polynomial, and b3, b2, b1, b0 and c3, c2, c1. And our next iteration value is 1, and then the x2 is 0.75, x3 is 0.68047 and x4 is 0.682340, x5 0.682328 and become constant to 6 decimal places. So, this is how the Birge-Vieta method can be employed. There are many other methods which are suited for polynomials. They are especially used for polynomials. Like this one method is known as Graffy's root squaring method. In the Graffy's root squaring method, what is done is, in case the polynomial's roots are very nearby, what it does is, as the name is root squaring, by squaring the roots are made to move away, they become distance is made between them, and then the methods can be employed to find their roots, and that is how, and again we can revert back. So, this is how the Graffy's root squaring method is used. Then there is another method which is known as Laguerre method, and many other methods are there. If you are interested, if a polynomial is known to have complex roots, there is another method which is called Bastow's method. It is based on the deflation technique. A quadratic factor comes out and ax square plus bx plus c roots can be determined by the formula, and deflated polynomial becomes a polynomial of degree n minus 2. Again quadratic factors can be taken out, and this is how the quadratic factors come out till we are left with a constant or we are left with a linear polynomial. So, Bastow's method is also employed in the case, and especially beneficially, it is especially beneficial when the polynomial has complex roots, and even Muller method is there, which is also used for determining complex roots. So, these are the many different special methods which are only applicable to polynomials, and even Newton-Raphson method can be used to find complex roots. Same formula with, in case of z, it can be used to find the roots of a polynomial. If a root is of multiplicity more than 1, in that case, means if a root is occurring more than once, maybe twice or thrice, the Newton-Raphson method slows down. It has its pitfalls. In that case, there is a modification of Newton-Raphson method which can be used to determine the roots of a polynomial. There is one more point at last which is worth mentioning, that some polynomials are very sensitive. So, a small change in their coefficients can alter the values of the roots. Just for example, if we take up x square minus 2x plus 1 equal to 0, it has a root 1 of multiplicity 2. But just suppose instead of taking this equation, the equation is x square minus 1.9999 x plus 1, then its roots become complex given by 1 plus minus 0.01 I. So, many times when you are solving, sensitivity also is to be taken into account. So, with this we end our module on the roots of polynomial. We have learned different methods of different closed type, open type, and also how to treat polynomials spatially. Now, in our next module, we will move on to the chapter on numerical differentiation, followed by the numerical integration. So, happy reading, bye bye till then, and thank you for visiting EPG Pathshala.